Hey, Sam. Sam, are you there? You there? Can you hear me? Sam, you may need to put it on computer audio and
Hello?
unmute your mic.
Hello?
Yeah, there you are.
Hey, sorry.
That's
My
all.
computer was acting up and my internet was also acting
Yeah,
up.
I couldn't remember. I thought maybe yesterday we ended up on phone call, so that could screw things up too. You get feedback if you have it on the wrong thing. In other words, if you have it on computer audio and we're talking on phone, that'll give you feedback. It makes it harder. All right,
hmm
so you're doing proving trig identities,
hmm
and you're doing it with double angles, which usually that's not where I start off with people. Usually the first place you start off with trig identities is the 11 fundamental trig identities. And then there's a whole bunch more. There's double angle identities also, and we're going to need that here. So I guess what I'm trying to say is you need to memorize these. There's no other answer. You just need to memorize.
hmm
What is sine of 2x? There's only one identity for that.
Is that the 2 sine theta cosine theta?
Yeah, hold on a second. Let me get to where I can write it. Well, hold on one moment. Let me, first of all, minimize that so it doesn't take up space. Yeah, exactly. 2 sine x cosine x. That's what that is. I'm dividing it by sine x. And I'm subtracting. What's cosine 2x?
I don't have that one down in my notes.
Well, there's actually 3 of them. And there's 3 of them because about a third of the time you need to use each of those 3.
hmm
Now, which one we're going to use here? Well, before we decide which identity to use, let's look at that left fraction. What can I do with that left fraction?
Can you cancel one of the signs out? So you just have sine
Uh-huh.
x
Yeah, so
cosine
now
x?
we have 2 cosine x minus something over cosine x. And that all is supposed to equal to secant x. Now, let's look at some choices we have for cosine, because there's really 3 choices. Here's what they are. We can use, I'm just going to list them down here. Cosine of 2x, and the one you use needs to be used in the context of the problem. So that's one of them. Here's another one. There's 3 of them. And finally, and it is worth noting something about these.
hmm
The first one is a function of sine and cosine, both squared. The second one is only a function of cosine squared. And the third one is only a function of sine squared. Now, if we look at what is going to allow us to solve this problem, well, first of all, I'm going to need a cosine in the denominator on the left, right?
Yeah.
Okay, so let's make it like that. In other words, what I've got now on the left is 2 cosine x.
Mm-hmm.
So let's stick a cosine x under that and then a squared over that. Now it's the same thing. I haven't changed anything. But now it gives me an idea of which identity to use. Which one should I use?
Would you use the second one down, the 2 cosine squared
In other words,
x minus 1?
once we know that that's what the numerator is going to look like, now I know that I've got to use 2 cosine squared of x minus 1. And notice what happens to my numerator.
Wait, so do you just have
Yeah,
minus 1?
everything goes away except plus 1.
And that's
And 1
equal
over
to
cosine x
Yeah.
is secant x. So this becomes 1 over cosine x, which is equal to secant x. And this is the way I usually do it, like that. In other words, you only work with one side of the equation, and you turn it into the other side. And once you do, then just draw an arrow to it.
Mm-hmm.
All right. Let's look at the second one. 8. Now, this doesn't have any double angles, but it's got a lot of squares. Okay. So the identities that we're going to use are this one, and what's the cotangent one?
Would it be 1 or cotangent squared plus 1, I guess, equals cosecant?
Yeah, in other words, it's
Squared?
the cofunction. In other words, if you remember this one is just the cofunctions of everything.
Mm-hmm.
Okay, so let's start substituting. For secant squared, I'm going to substitute that. So that becomes
For
tangent.
both of them?
What's that?
For both of them?
Well, we'll just take it as we come. Now, what is secant squared minus 1 equal to?
Just tangent squared x.
Okay, so that's what I make the bottom. And I'm just going to leave that alone for the moment because that turns into something. Separate that into 2 fractions. Well, hold on a second. Let me have a look at this. I feel like I'm making a mistake somehow. No, I'm not. Separate that into 2 fractions. What do you get? When I say that, I mean that's 1 fraction. That's another fraction.
I guess tangent, you could do sine over cosine.
Well, let's just do it one step at a time. Tangent squared over tangent squared is what?
1.
What's 1 over tangent squared?
Isn't that, I don't know actually. Wait, that's cotangent, right?
Okay, so that's what the left side becomes. There's our identity. There's the right side. In other words, if I substitute the identity for that, I got cosecant squared x. Understand?
Mm-hmm.
Let's go further. I assume there's some underneath this. Yeah.
Mm-hmm.
All right. Most of these identities, it's fairly obvious how you proceed, but these are different. Whenever you see something
Cubed.
whenever you see cosine x plus 1, cosine x minus 1, sine x plus 1, sine x minus 1, whenever you see anything like this, think of multiplying that by the conjugate. Notice what you're going to get. You're going to get cosine squared x minus 1, which can be replaced with a single term. That is the key. And so whenever you see that, or that, think about multiplying top and bottom by the conjugate. It's probably the most difficult trig verification type problem, because it's not at all obvious that one would do that. You wouldn't do that unless you knew to do that. So that's why I'm putting it to you like that, is whenever you see that, know that you're probably going to have to multiply by the conjugate. So I'm going to multiply, and remember, I'm just going to work with the left side, okay? So here's what I'm going to do. Cosine x plus 1 over sine cubed x. I'm going to multiply top and bottom by the conjugate of the top. Now that's the number 1. So I can multiply any fraction by the number 1. And what that gives me on the next line is cosine squared x minus 1. Because this is difference of squares, and you factor difference of squares into plus 1 and minus 1. So going back the other way is not that hard. Okay, now in the bottom, let's leave it unmultiplied, which is usually the correct thing to do. Don't distribute this. And you'll see why in a second. What can I replace the numerator with?
Let's see. You could do it sine squared.
Minus 1, exactly.
You could do it sine squared.
That's sine squared. Now, notice why I didn't distribute the bottom, because I can cancel that with all but one of those. So now what do I have? I have 1 in the top, and in the bottom I have sine x times cosine x minus 1. Well, what's that?
Isn't that cosecant?
It is. Unfortunately, that isn't what they gave us. I lost a negative sign somewhere. What did I do? Let's see, I multiplied by cosine x minus 1. There's the cosine of x minus 1 that's still there. That's cosine squared minus 1, which is, that's not sine squared, that's negative sine squared. Here, let's go back a step. In other words, and incidentally, on these trig verifyings, they will always be correct. They're never going to give you one that isn't. Definitely that. But let's look at our trig identity. Sine squared of x plus cosine squared of x equals 1. Therefore, what is cosine squared of x minus 1 equal?
Negative sine squared?
Negative sine squared. That's what I dropped, was the negative. So if I make that negative sine squared of x, now I can cancel that with the numerator, and I end up with negative 1 over sine x times cosine x minus 1. That is negative cosecant. So that's how they get the cosecant in the numerator. But notice their denominator is 1 minus cosine x instead of cosine x minus 1. Well, guess what? A minus b is always equal to minus b minus a, no matter what a and b are. In other words, the difference between 1 minus cosine x and cosine x minus 1 is negative 1. So, in other words, I can now say that this thing is equal, the numerator I'm not doing anything with, that's negative 1 over sine x, and this I'm going to say is 1 minus cosine x, and then I change that to a positive 1. So this over here is the same as this right here. And now you can take that 1 over sine x, turn it into cosecant x, and that's the identity. And we have exactly the same thing.
Okay.
That one was a little tougher. Let's just review that principle because this is one that is not always obvious. Tell me what this equals. Negative 1.
Yeah.
The reason is because I can write the numerator as 3 minus x, and I can write the denominator as minus 3 minus x. Notice that that denominator is exactly the same as that denominator. They are not different. If I distribute that negative sign, I get x minus 3. Okay? Now, that 3 minus x cancels with that 3 minus x, and you're left with minus 1. So this is an important concept in algebra and trig. In other words, they probably tried to teach it to you in algebra, but not everybody gets it. It's different. And but then when you get to trig and you start trying to prove some of these identities, you have to know these kind of things.
Wait, so why were you able to put the negative outside the 3 minus x again on the right side?
Okay. Here's what I said. X minus 3 is equal to minus 3 minus x. Now, go to the right side, distribute that negative sign, what do you get?
On the right side?
Uh-huh.
You get, oh, okay, you get positive
3 plus x.
Oh.
Which is the same as x minus 3.
That's the same thing.
Uh-huh. So that's why a minus b divided by b minus a is always equal to negative 1.
Okay, I get it.
So whenever you're trying, if you end up with cosine x minus 1 instead of 1 minus cosine x, is all you are is off by a negative sign. That's it. So you just have to go back and figure out where you lost your negative sign. And that was easy enough to do. I made the mistake, and I just had to go back, and because I had said cosine squared minus 1 was equal to sine squared, but it was not. It was equal to negative sine squared.
Mm-hmm.
All right, number 10. Again, nothing, no double angles here. What's that equal to? Whenever you see squared minus 1 or plus 1, you know you want to replace it with the Pythagorean identity.
Is that just sine squared?
That's negative sine squared.
Negative sine?
Okay, here's the identity. Sine squared of x plus cosine squared of x equals 1.
Oh, wait, no, never mind. I see.
So if I bring the 1 over and the sine over, got to be negative. Negative sine squared of x In other words, I don't want to make the same mistake I made last time. Now, look at this. That is minus sine x times sine x, correct?
Mm-hmm.
All over cosine x. And if I look at that alone, what is that?
Oh, that's tangent.
Ah,
But if you use the other one, would you have negative tangent and then regular sine
oh, there's
squared?
a negative sign right there.
Mm-hmm.
There's my negative sign. In other words, I'm there. Sine x over cosine x is tangent x. Now I have negative sine x tangent x. Doesn't matter the order these are in. You can put those in either sine x times tangent x or tangent x times sine x.
Okay.
Okay? Most people hate these identities. I love them. I don't know why. I just think they're fun. They're kind of like puzzles. I will say this. They serve no other purpose other than to get you to learn your trig identities. There are no real life problems where you ever have to do this. And that's why they don't let you use algebraic techniques to solve them. In other words, I cannot cross multiply this next one. They don't want you to do that. They want you to take the most complicated side, which is almost always the left side, and they want you to turn it into the right side. That's all they want you to do. You can't do things like cross multiply, or you can't use normal algebraic techniques. So let's take that and see if we can make it look something like that. So let's start with the numerator. What is our trig identity that has secant squared in it?
Let's see. Secant squared. Isn't that tan squared plus 1?
Uh-huh. So what's secant squared minus 1 equal?
Negative tangent squared.
If I take
Minus
the 1 on the other side, I'm just left with that.
Oh, yeah.
So that's tan squared of x all over sine x. Let's leave it like that for a moment. And we're trying to get that. Well, what's tangent in terms of sine and cosine? The other rule for these problems is if all else fails, convert everything to sines and cosines and proceed forward.
Mm-hmm.
So if I convert that to sines and cosines, what do I get?
Isn't it just sine squared over cosine squared?
And I still have that sine x down there, right? This one here. Well, that sine x cancels with that exponent. And now I got sine x over cosine squared of x. Well, I got my numerator, right?
Mm-hmm.
Well, what's cosine squared of x in terms of that? Is it that? If it's that, then we're home.
Okay.
And it is that. In other words, cosine squared of x is 1 minus sine squared of x. And that's exactly what we were trying to prove.
Okay.
So I think we've pretty much covered all of the various techniques that you use here.
Mm-hmm.
The only one that is strange is when you have something like that. And that.
Mm-hmm.
Now, for this problem here, I'm not going to go through it because we're out of time, but just find a least common denominator. And that least common denominator is going to be 1 minus secant squared of x, and that happens to be negative tangent squared.
Mm-hmm.
So always look for these 1 minus or 1 plus, and always look to be multiplying by the conjugate. Well, if we go to find a least common denominator, we multiply them together. So it's the same thing as multiplying by the conjugate, and that will lead you to the answer.
Mm-hmm.
In other words, just add those two fractions. Find
Okay.
a least common denominator. But that's these identities. And like I said, there is only one purpose. And usually it's to teach you the 11 primary identities. Tonight, they actually added the double angle identities also. So there were 13 things you had to remember. But I'm sure by now you realize that trig is all about memory. More than any other math, more than geometry, more than algebra. You got to
Mm-hmm.
memorize stuff. That's just the only way to get through it. You got to know these basic identities. And so what some clever mathematician did was come up with a test like these, proving trig identities. And the only way you can do it is if you really know your identities good. And then you get good at it. And by the time you've spent an hour proving trig identities, you know your identities really good. That's just what results. In other words, all this is a drill. It's like somebody sat there with flashcards on all your identities and wants you to know what they are. It's a little more complicated than that because you do have to know some of these tricks about multiplying by the conjugate and things like that. But that's all that is. The main purpose here is to make sure you know your 11 basic identities plus the double angle ones for the first problem we did. Sam, you got any questions?
No, I think I'm all good.
Okay. It feels to me like you have a pretty good feel for these. And like I said, it's all memory. So I will talk to you next time.
Thank you. Bye.